Problem 11, just to give a little explanation of what's going on here. Let's assume that we have a section of a big wall. Now, let's say that section is, and the wall is in the previous problem. We have temperature T1 on this side, T2 on this side. Let's say the wall is divided into equal areas. And this is only a section of a big wall, and that the wall has been, this side has been held at temperature T1 for a long time, this one at temperature T2, so we have this nice linear temperature gradient across here. Each of these sections we would expect to conduct the same energy per unit of time. That is, if this one conducts 100 joules in a minute, then we expect this one and this one and this one to also conduct 100 joules in a minute. So that the total conduction over the 4 segments would be 400 joules in a minute. Each section conducts the same energy per unit of time, and it follows then that the rate of energy flow is proportional to the area. The more area we have, the more little segments we can, or the more little squares we could draw, and the more energy would flow through all those little squares. So the rate of energy flow should be proportional to the area of the wall. We're also going to assert that the rate of energy flow is proportional to the temperature gradient. So it's proportional to the cross-sectional area and to the temperature gradient. Now we write the proportionality. We say that the rate equals the delta Q over delta T, and I put absolute value signs around this just so we don't get too confused about pluses and negatives. The rate, we're just going to be interested in the magnitude of the rate. We know it goes from hot toward cold. We can deal with that. The rate's the magnitude of the delta Q, and delta Q is something that we use for the change in the thermal energy, the flow of thermal energy. Okay? And delta Q over delta T is, of course, the rate at which thermal energy flows. And we're going to say that that rate is proportional to the area and the temperature gradient. Now I put absolute value signs around the temperature gradient also, so we don't have to worry about signs here, because that gets a little bit confusing and we don't need to distract ourselves. K is our proportionality constant. To say that the rate is equal to K times the area times the temperature gradient is to say that the rate is proportional to the area and the temperature gradient. Now, problem 11 asks us to find K, given the area, information for the temperature gradient, and the rate. So how do we find K? Well, we solve this for K. We divide by A and we divide by the temperature gradient. So K is the rate divided by the area here and divided by the temperature gradient, which goes under here. Okay, and that equals then the rate over the area multiplied by the temperature gradient. So if we know the rate, the area, and the temperature gradient, we easily find K, and we call K the thermal conductivity of the material. The units of K, well, K is rate of temperature flow, which is delta Q over delta T, which is going to be measured in joules per second, okay, or watts. So the rate of flow is in watts. The area is in square meters, and the temperature gradient, well, it's a delta T over delta L, that's Celsius degrees over meters. So it's watts over meter squared, Celsius degree over meters. Now the meter here will divide into the meter squared, leaving us a meter. We have then watts per meter Celsius degree, and that's an acceptable unit for K. This is even acceptable. The simplest in terms of kilograms, meters, and seconds is this, and you can do the simplification. A watt is joule per second, which is a newton meter per second, which is kilogram meter per second squared, meter per second squared, etc. And you can work all that out. You just write it out if you know the meanings of these units. And this is what it simplifies out to.